Hi everyone, my name is Sam Connerly, and today we're going to be looking at Physics 2, Lab 4, circuits and capacitors. So first, let's talk a little bit about the lab. The purpose of this lab is to predict the behavior of circuits with resistors both in series and in parallel. We're going to calculate some values for the conventional current and potential differences. We're going to observe behavior of resistors and capacitors. And in order to do this, we're going to be using a virtual site to create our circuit and our system. Then we're going to compare these findings with our calculations to see if they match up. So first, let's talk about some key concepts. First, there's the node rule that the sum of currents from each junction will be equal to the current of a junction. This follows the conservation of charge, I in equals I out. We're also going to be looking at the loop rule, where the difference in potential energy for a round trip path is zero, which is aligned with the conservation of energy. Let's look at some of the formulas we're going to be using for calculating resistance. First is that resistance in any component is going to be equal to Ohm's law. That's the first equation you can see down there. Second is the equivalent resistance of resistors in parallel. It's going to be the sum of 1 over Rn. That's the second equation you see. And then we have the third equation, that this is the equivalent resistance of resistors in a series, and it's just the sum of Rn. We also need to look at capacitance. How much charge can be stored in a capacitor. This is going to be based on potential difference, which we'll be using some tools to calculate. And it also factors in the size of plates and the separation distance between the two plates. We can see this in the equation below. So the first instance we're going to be looking at is a simple circuit. Here you can see that we have two batteries, both 1.5 volt, two resistors on the right-hand side, one being 47 ohms and one being 100 ohms. We're going to put two ammeters in it, and we see that our predicted current is going to be 0.02. And from the results of this simulation, we can see that the simulated current is also 0.02. And if we were to reverse the ammeter, it would be negative 0.02. Now we're going to place a voltmeter in order to find the voltage of the system. We're using the same batteries and the same resistors, but this will allow us to calculate the predicted potential difference in our system. We can see that this is 3 volts, and this is equivalent to simulated and predicted values. We can also see that it's the sum of the two batteries we have in the system. And there's no current currently flowing because the circuit is open, which is what allows us to put our voltmeter in. So now we're going to look at potential differences. For this part, we're going to take the potential difference at various spots along our system. We'll be able to perform some analysis based off those results. So from the A to B point, we see that it's 3 volts, B to C, it's 0, C to D, negative 0.96, D to E, it's 0, E to F is negative 2.04. The rest of the points will measure out at 0 volts. We can see that this follows the loop rule because the sum of all of these potential differences is equal to 0, and we're making a round trip path with these points, so that checks out. Now we're going to look at a meter in parallel. We're using a similar setup with two batteries and two resistors. The batteries both at 1.5 volts, resistor 1, resistor 2 being the same as last time. But we're going to see a current increase of 0.04 and a simulated increase of 0.04 as well. This is because that some of the current doesn't need to go through the junction and it creates a higher current. So we're going to calculate the resistance for our resistors. We see that it's a little higher, and we'll go into that in a little bit, but we found those using the formulas below, using Ohm's law. Now we're going to look at an RC current circuit. We have one battery, two resistors, similar to last time. We're going to look at the discharging rate, charging of a capacitor with resistors 10 ohms and 20 ohms. We see that with 10 ohms, the discharging is quicker. And this is because with greater resistance, the charge moves slower. We're also going to measure now what happens when we discharge the voltage and how that changes over time. We're going to use these formulas below. We're going to plot the natural log of V over V naught, and the slope will be negative 1 RC, and we'll solve for RC. We put that out on this graph. We can see our slope and our RC calculations using those formulas from below. We see some discrepancies here, maybe due to some inaccuracies with the meter, could be issues with decimal places, discrepancies within the code, maybe just human error from me just taking too much time when calculating the time graph study. And if we did this lab in real life, the main thing is that resistance would be non-zero for the wires and emitters. This would cause some issues with the resistance we calculated. And this would also cause some effects with the capacitor charging.